We'll start in 1 minute. Today we'll continue the test 3 review. Test 3 is on Friday. I'll send a Zoom link for the test tomorrow. Okay, we're at this polar equation, r equals 1 plus 2 times sine of theta. And first we'll graph the Cartesian equation, rectangular coordinates. So from 0 to 2 pi, when theta is 0, the r value is 1. And the amplitude is 2, so when theta is pi over 2, the r value is 1 plus 2 times 1, or 3. And then at pi, the r value is 1 again. At 3 pi over 2, sine of 3 pi over 2 is -1, so 1 minus 2 is -1. And then at 2 pi, the r value is 1 again. So the graph looks something like this in rectangular coordinates. Okay, we'll use the rectangular coordinates graph to graph the polar equation. Okay, when theta is 0, the r value is 1. When theta is pi over 2, the r value is 3. So the graph looks something like this. At theta equals pi, the r value is 1. So the graph comes back down to the x-axis. And then notice that between pi and some other theta value, the r values switch from positive to negative. So we'll figure out what those theta values are, where the r value is 0, in a minute. But between pi and whatever that is, the r value is 0. And then between this theta value and 3 pi over 2, the r values are negative. So at 3 pi over 2, r is -1, so we have to plot this point, which is opposite, on the opposite side of the origin. And what we get is an inner loop from 3 pi over 2 to this theta value. The r values are negative again, so we complete the loop and go back to 0. And then from this theta value to 2 pi, the R values are positive again, so they're looks something like this. So we have this inner loop. So we can determine what the theta values are when the R value is 0. So in the equation, we just replace R with 0. So we get 0 equals 1 plus 2 times sine of theta. Subtract 1 and divide by 2, we get sine of theta is equal to negative 1/2. And we know that sine is negative in the third and fourth quadrants, so the theta values are 7 pi over 6 and 11 pi over 6. Okay, the next problem. Let C be the curve defined by the equation the quantity x squared plus y squared squared equals 2x squared minus 2y squared. Find the equation of C in polar coordinates, and then find the total area bounded by C. Okay, so we know that x squared plus y squared is r squared, and x is r times cosine of theta, and y is r times sine of theta. So our first substitution, replace x squared plus y squared with r squared, so we get r squared squared, and then that's equal to 2 times x squared, but x is r times cosine of theta. So this is equal to 2r squared cosine of theta squared, and then minus 2y squared, but y is replaced with r sine of theta, so this is minus 2r squared times sine of theta squared. So on the left-hand side, r squared squared is r to the 4th, but we'll just divide every term on both sides by r to the 2nd to get this equation. R to the 2nd equals 2 times cosine of theta squared minus 2 times sine of theta squared. We'll use an identity. We'll factor 2 out, and then we'll use the identity that cosine of theta squared minus sine of theta squared is just cosine of 2 theta. Okay, so what we get is r squared equals 2 times cosine of 2 theta. Okay, notice that r squared has to be greater than or equal to 0, but it's defined by 2 times cosine of 2 theta. And we know that if we were just to graph r equals 2 times cosine of 2 theta, in some places it's negative. So we're only going to use the part of the graph of 2 times cosine of 2 theta where it's positive, because r squared has to be non-negative. So we'll graph r equals 2 times cosine of 2 theta. just to see where this where this is positive or non-negative. So we'll go all the way from 0 to 2 pi with 2 periods. And amplitude 2. So that's pi over 4, pi over 2, 3 pi over 4, pi, then 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. And over here I have negative pi over 4. So first let's just go from 0 to 2 pi. We start out at when theta is 0, the R value is 2. At pi over 4, 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0. Then at pi over 2, 2 times pi over 2 is pi. Cosine of pi is negative 1, so we have negative 2 down here. And then we'll just sketch the rest of this graph. Okay, going to the left, the graph would cosine of 2 times negative pi over 4 is 0. Okay, so what we're going to do is sketch the R squared based upon the R equals 2 times cosine of 2 theta. So if we subdivide the region, this is theta equals pi over 4. This is theta equals negative pi over 4. Okay, so we're going to use the part of the graph that's above the x-axis to graph r to the second. So at negative pi over 4, the r value is 0. When we get to 0, the r value on this graph is 2, but if it's r squared, it has to be the square root of 2. So just note that we're going to use r equals the positive square root of 2 times cosine of 2 theta. So that's why we have to reject the negative values where 2 times cosine of 2 theta is, because the square root of a negative is non-real. So between negative pi over 2, negative pi over 4, and 0, the graph of r squared goes to the square root of 2. And then at pi over 4, it's back to 0. And then we can graph r equals the square root of 2 times cosine of 2 theta between pi over 4 and 3 pi over 4, because these are negative numbers. And so we pick it up again at 3 pi over 4, and we're 0 here, and then by the time we get to pi, we're at the positive square root of 2. On the x-axis, this number is negative square root of 2. And then from pi to 5 pi over 4, we go back to 0. Then for the negative values, we can't include anything else on the graph. And then from 7 pi over 4 to 2 pi is just a retracing of what we did on from negative pi over 4 to 0. Okay, so this is the graph of r squared equals 2 times cosine of 2 theta. And we want to find the area. So we can just set up a fairly simple integral. The area of each of those two loops are supposed to be identical. My picture doesn't look like it. So if we just use one integral from theta equals negative pi over 4 to pi over 4 and find the area of this loop, and then multiply that by 2, that will give us the total enclosed area. Okay, so the total area, we have 2 times the integral from negative pi over 4 to pi over 4. And the integrand for finding areas enclosed by polar curves is 1/2 r squared. Well, r squared is 2 times cosine of 2 theta. So 1/2 r squared is just cosine of 2 theta. And so all you have to do is evaluate this integral, and that will give you the area of both loops. I guess we can take it one step further. An antiderivative of cosine of 2 theta is 1/2 times sine of 2 theta. And then evaluate that between theta equals negative pi over 4 and pi over 4. Okay, let's move on to the next page. Number 9. Find the area of one loop of the polar curve r equals 2 times sine of 2 theta. So let's revisit problem number 7, part A, briefly, because on this one, we did the graph of r equals sine of 2 theta. The only difference between this one and the one in number 9 is that we have a 2 times sine of 2 theta. Otherwise, the graph is similar. And so we can use this graph to see what interval we need for one loop. So we can use the interval from 0 to pi over 2 to find the area of one loop. Okay, so the area formula, we alluded to it in the previous problem, but the area enclosed by a polar curve from theta equals alpha to theta equals beta, the integrand is 1/2 r squared d theta. Okay, so for this one loop occurs between 0 and pi over 2. So we have 1/2, and then we're going to square what r is. We're squaring the quantity 2 times sine of 2 theta. When we square 2 times sine of 2 theta, we'll get 4 times sine of 2 theta squared, and then times 1/2. That will give us 2 times sine of 2 theta squared. Then we'll replace sine of 2 theta squared with identity 1/2 minus 1/2 times cosine of 4 theta. Then if we distribute multiplication by 2, in the integrand, we get the integral from 0 to pi over 2 of 1 minus cosine of 4 theta d theta, and then an antiderivative of 1 minus cosine of 4 theta with respect to theta is theta minus 1/4 times sine of 4 theta. We evaluate this from 0 to pi over 2. So we can tell by looking, sine of 4 times pi over 2 is sine of 2 pi. That's going to be 0. And then when theta is 0, sine of 0 is 0. When theta is 0, this is 0. So there's only one term that's non-zero when we evaluate this, and it will be equal to pi over 2. Okay, let's look at the next problem, number 10. So there's not a lot of room to do part A for this one. So I'll copy some stuff down from number 10, part A, and do it on separate paper. So find the tangent line to C that corresponds to theta equals 0. Okay, so we need to find dy dx, and in the numerator that's dy d theta, and we divide that by dx d theta. So we're using y equals r times sine of theta and x equals r times cosine of theta, where r is a function of theta, so we use the product rule. The derivative of y with respect to theta using the product rule is dr d theta times sine of theta, and then plus r times cosine of theta. And the denominator, dx d theta, so r is a function of theta, so we use the product rule again, so we get dr d theta times cosine of theta, and then minus r times sine of theta. But since r is equal to e to the k theta, dr d theta is k times e to the k theta. And then we just make substitutions. So dy dx, dr d theta is k times e to the k theta times sine of theta, and then plus r times cosine of theta, but r is e to the k theta. In the denominator, dr d theta again, so k times e to the k theta times cosine of theta minus r times sine of theta, e times k theta times sine of theta. Notice that every term has e to the k theta in both the numerator and denominator. So if we divide, well, if you factor out e to the k theta from both the numerator and denominator, and then e to the k theta divided by e to the k theta is 1, we're just going to be left with k times sine of theta plus cosine of theta in the numerator, and k times cosine of theta minus sine of theta in the denominator. And at theta equals 0, dy dx, which is going to be the slope of the tangent line that corresponds to theta equals 0. So sine of 0 is 0, cosine of 0 is 1, so the numerator will just be 1. And in the denominator, when theta is 0, k times cosine of 0 is k times 1 minus 0. And so 1 over k is the slope of the tangent line. And then we have to find the point that the tangent line passes through when theta is 0. So in general, x is r times cosine of theta, but r is e to the k theta. So in this case, x is e to the k theta times cosine of theta, and y is e to the k theta times sine of theta. So at theta equals 0, the x coordinate is e to the 0 times cosine of 0. 1 times 1 is 1. And the y coordinate, when theta is 0, e to the 0 times sine of 0 is 0. So the ordered pair xy is 1, 0. The slope is 1 over k. So the equation of the tangent line is y minus 0 equals 1 over k times x minus 1. Or just y equals 1 over k times x minus 1. Okay, let's do part B of number 10. I think we have enough space for part B. Find the length of C for values of theta between 0 and 2 pi. Okay, so the arc length formula for polar curves, L equals the definite integral from theta equals alpha to beta of the square root of dr d theta squared plus r squared d theta. Okay, so as we saw earlier, dr d theta is just k times e to the k theta. So when we square that, we'll get k squared times e to the 2k theta. And r squared is just e to the 2k theta. And so our arc length antiderivative, or sorry, arc length integral will be from 0 to 2 pi. The integrand is the square root of k squared e to the 2k theta plus e to the 2k theta. We can factor out, inside the square root, we can factor e to the 2k theta from both of the terms. And then when we take the square root of that, we'll get this integral. The square root of e to the 2k theta is just e to the k theta. And then that's multiplied by the square root of k squared plus 1. The square root of k squared plus 1 is just a constant, and an antiderivative of e to the k theta with respect to theta is 1 over k times e to the k theta. So I'll just write down one more step and leave the rest of it for you. So we have the constant square root of k squared plus 1, and then times 1 over k times e to the k theta, and evaluate that from theta equals 0 to 2 pi. Okay, to find the area enclosed by the curve C on the rays, or between the rays, theta equals 0 and theta equals pi over 2. So the formula for area enclosed by a polar curve, we've seen this before today, the integral from theta equals alpha to beta of 1/2 r squared d theta. Okay, so since r is e to the k theta, r squared is e to the 2k theta, and our integral is between the rays theta equals 0 and pi over 2. And so 1/2 times e to the 2k theta. So this is a pretty simple integral to evaluate. We have 1/2, and then an antiderivative of e to the 2k theta is 1 over 2k times e to the 2k theta between 0 and pi over 2. So 1/2 times 1 over 2k is just the constant 1 over 4k. And then first replace theta with pi over 2. 2k times pi over 2 is e to the k pi. And then minus e to the 0 minus 1. Okay, the next problem, we're just going to convert this equation into polar coordinates. So on the left, start with 1/2 times the logarithm. Replace x squared plus y squared with r squared. And on the right-hand side, we have the arc cosine of something. So in the numerator, we have x. So we replace x with r times cosine of theta. And in the denominator of the arc cosine argument is the square root of x squared plus y squared. So that's the square root of r squared. We'll just write r. And then this is multiplied by log of a. Using a property of logarithms, 1/2 times the logarithm of r to the second. That's the logarithm of r to the second to the 1/2. And then we have the arc cosine of cosine of theta times the logarithm of a, because the r's cancel. The logarithm of r to the second to the 1/2, using a property of exponents, we multiply 1/2 times 2, so we just get the logarithm of r. And the arc cosine of theta is just theta, because the arc cosine is the inverse of cosine. So theta times the logarithm of a, and then the logarithm of r equals the logarithm of a to the theta. And since the logarithmic function is 1-to-1, this must mean that r is equal to a to the theta. So that's the polar equation, which looks a lot simpler than the equation from which it came. Okay, let's move on to the next page. Write the first 4 terms of the following sequences and indicate which ones converge. So when n is 1, we get 5 to the 1/1, or 5, then 5 to the 1/2, 5 to the 1/3, 5 to the 1/4, and so on. So the limit as n approaches infinity of 5 to the 1/n, we can write this as 5 to the limit as n approaches infinity of 1/n. And the limit of 1/n as n goes to infinity is 0, so the limit is 5 to the 0, which is 1. Okay, this one, the first 5 terms, so 1 minus 1/2 is 1/2. Sorry, I did that wrong. When n is 1, 1 minus 1/n is 0. Then when n is 2, 2 minus 1/2 is 3/2. 3 minus 1/3 is 2 2/3, or 8/3. When n is 4, 4 minus 1/4 is 15/4. And we can tell as n goes to infinity, n minus 1/n goes to infinity, so the sequence diverges to infinity. Yeah, on this one, notice that if we simplify first before doing anything else. N plus 1 squared is n squared plus 2n, and then plus 1, and then minus 1 divided by n. Since 1 minus 1 is 0, we get n squared plus 2n over n. Divide by n, we get b sub n equals n plus 2. So I'll leave the rest of that for you to find the first four terms. Oh, let's find the first one. When n is 1, the first term is 3. And then this, when you take the limit of this sequence, it diverges to infinity. So it doesn't converge, it diverges. Okay, write the following series using sigma notation. So on this one, if we start at n equals 1 and go to infinity, it alternates from minus to plus, minus to plus. So we have negative 1 to the n plus 1 because the first term is positive. And then we multiply that by 1 over 2n. The denominators are just multiples of 2. Okay, for the next series, if we start at n equals 1, in the denominator, notice that in each denominator, the factor on the left increases by 1. So the left factor corresponds to n plus 1. The second factor in each denominator increases by 2. So that means we have to have 2 times n. And let's see, when n is 1, 2n plus 1. So this is the sigma notation for this series. And the next one, evaluate the series, 5 minus 10 thirds plus 20/9 minus 40/27. You can verify that the common ratio, if you divide one term by the term immediately to the left, such as negative 10 thirds divided by 5, and then simplify, negative 10 thirds times the reciprocal of 5 is negative 2 thirds. So the common ratio is negative 2 thirds. So we can write this using sigma notation from n equals 1 to infinity of 5 times the common ratio negative 2 thirds to the n minus 1. You can verify that this is the correct formula by finding the first few terms of the series. But this is a geometric series. So if the common ratio is between negative 1 and 1, then this will converge to a over 1 minus r. So in this one, the value of a is 5. The common ratio is negative 2 thirds, so in the denominator is 1 minus negative 2 thirds. So we get 5 divided by 1 plus 2 thirds, which is 5 thirds. And this is 5 over 1 times 3/5. So the series converges to 3. Okay, in the next example, find the sum of the series. The terms are 1 over n times n plus 1. So we'll use partial fractions on this one. And we'll see if we have a telescoping sum. So the two factors in the denominator are n and n plus 1. So we write a over n plus b over n plus 1. So with a common denominator, this becomes an plus a plus bn all over n times n plus 1. This has to be equal to 1 over n times n plus 1. So the only constant in this numerator is a. So a has to be 1. And a plus b has to be 0. So that means b has to be negative 1. So we can write the terms of the series as a difference of two terms. So 1 over n and then minus 1 over n plus 1. We'll write a few of the first few terms in the sum. And we should be able to tell what's going to happen. So when n is 1, we get 1 over 1, which is 1, minus 1 over 1 plus 1 is 1 minus 1 half. This corresponds to n equals 1. The next term in the series, when n is 2, is 1 half minus 1/3, corresponding to n equals 3. The term in the series is 1 over 3 minus 1 over 4, and so on. So the terms, pairs of terms add up to 0, minus 1 half, plus 1 half, then minus 1/3, plus 1/3. And this will continue forever. So the series converges to 1. So another way to think about this is to write down the partial sums. S1 is 1 minus 1 half. The second partial sum is 1 minus 1 half plus 1 half minus 1/3, which is 1 minus 1/3. And so on. And then you'll see that the pattern is Sn is equal to 1 minus 1 over n plus 1. And then when you take the limit of the sequence of partial sums, you'll get 1 for the limit, because 1 over n plus 1 goes to 0. Okay, the next one is just a geometric series. To help, you can re-index. So let's just write out the first few terms, starting with n equals 3. So when n is 3, the term is 2 over 5 to the 5th. And then when n is 4, we get 2 over 5 to the 6th. When n is 5, we get 2 over 5 to the 7th, and so on. If we factor 2 over 5 to the 5th out of every term, we'll get 2 over 5 to the 5th times the quantity 1 plus 1/5 plus 1 over 5 to the 2nd, and so on, plus 1 over 5 to the 3rd. Okay, so we can see that it's a geometric sequence, and we can reindex in the sigma notation, we can start at n equals 1. And the a term is 2 over 5 to the 5th. The common ratio is 1/5, so we write 1/5 to the n minus 1. And then use the geometric series formula. Since the common ratio is between -1 and 1, it converges to 2 over 5 to the 5th in the numerator divided by 1 minus 1/5. So 2 over 5 to the 5th, 1 minus 1/5 is 4/5. Dividing by 4/5 is equivalent to multiplying by 5/4. So 1 factor of 5 cancels, 1 factor of 2 cancels, so we just get 1 over 5 to the 4th times 2, which is 625 times 2, or 1250. Okay, we're out of time. I'll just make one mention. Since the limit of -1 to the n times n over n plus 2, as n approaches infinity, this does not exist. So the test for divergence says the series diverges. Okay, that's all for today. Tomorrow I'll send the Zoom link for the test on Friday. Go ahead and sign in for attendance.